Hello everyone, my name is Feline Hermans and I'm the author of the Manning book, The Programmer's Brain. And in today's session, we're going to look at one chapter of my book concerning a technique I call cognitive refactoring. I'm on Twitter as well, by the way, so if you want to tweet about this session, my Twitter handle is @Feline. In order to understand how I came to research cognitive refactoring, we have to go back into my personal history a bit. We have to go back to the year 2013 when I started to teach programming to children. And I didn't have a background in education. I had a background in programming. I just finished my PhD in software engineering. So I was really excited to teach these kids programming, but I didn't really know that much about teaching, which I thought at the time wasn't really an issue. I was like, well, I know programming and these are 10-year-olds, so how hard can it be? Well, it turns out it can be actually kind of hard because I didn't know anything about learning and these kids were struggling. They were confused by syntax. They didn't really know how to grasp new concepts and I didn't know how to help them. And because I didn't really know that much about teaching, I didn't know how to help them specifically. But it made me really interested in how people learn because these kids voluntarily came to the community center on their free Saturdays and yet they were frustrated and yet they were learning. So I was like, this is on me. I need to get better at knowing how to teach, knowing how people learn. And then ultimately this became my book because I started to learn so much about how people learn that I thought other people might benefit from what I learned as well. So I started to dive into cognitive science, the science of how people learn. And there's a bunch of things I took away from my explorations that I want to share with you today in this session, as well as in the book. So what actually happens in your brain if you read code? Let's look at what happens in your brain when you process information in general. So this is not about code specifically, it's about how we process anything. If information comes into your brain through your senses, your eyes or your ears, firstly, this information is stored in the short-term memory, which is a little bit like an I/O buffer. It's kind of small and it stores your information only briefly. Research into the short-term memory is very old, actually. We've already known since the 1950s, since the work of George Miller, that the short-term memory is very, very, very small. And we mean actually really small. So the human short-term memory can only hold between 5 and 9 elements at the same time. So that is very tiny. And just to give you a sense for how tiny this actually is, we're going to do a little memory experiment. So I'll show you a sentence very briefly, just like half a second. And it's your goal to remember this sentence, just so you can explore how little fits in your short-term memory. Here we go. Be ready? So that was like really hard, right? The information couldn't even trickle in your brain, in your short-term memory, and then already the time was up. And maybe you guessed that I was tricking you a little bit somehow, right? Because this was a sentence, yes, but it was sort of a weird sentence. I only talked about half of the picture so far. So let's zoom into what happens in your brain a little bit more. So once information is in your short-term memory, it is then further processed by something that we call the working memory, that you can see a bit as a processor in a computer that isn't just remembering like the short-term memory, but processing the information as well. Your working memory works together with your long-term memory. So your long-term memory is like an angel on your shoulder that says, hey, working memory, if you're thinking about this, here's some information that might be relevant for you. It's a little bit like Amazon recommends, hey, if you bought this book, maybe you also like this book. Hey, if you like this information that you're thinking about, maybe you would like this information as well. So your long-term memory very, very much supports your working memory in processing new information that you see. And just to experience that also, we'll do 2 more memory exercises with new sentences so you can see just how much your long-term memory helps you to process information. So here's another sentence. That was probably easier, right? It was still hard, but at least you could make some sense of what was happening there. You saw the letter maybe A and B and M. This was your long-term memory. Your long-term memory was saying, hey, these are letters. I know these letters. What do you want to know about these letters? And we'll do one more exercise, just so you can see that it is actually possible to remember such a short sentence in a very, very brief period of time. So are you ready for the next sentence? Here it comes. So that was probably rememberable and processable, right? Because these are familiar things. You know what a cat is, you know what loves is, and you know what cake is. So cat loves cake. In just half a second, you're able to see this, store it in your long-term memory, and process it with your working memory. That is because these things, cat and loves and cake, are actually retrieved from long-term memory. So your short-term memory here isn't doing, half a circle and a circle with a stick and then a cross and then a stripe and then another circle. No, your working memory is activated and your long-term memory is like, I know these letters. I know what that is. That is a cat. And then in your short-term memory, you just store cat. You don't store the individual letters or characters or the words. You just store the concept. And then this is just 3 things. So that easily fits within the limits of your memory. So the takeaway so far is that the more you know, the more you see, right? If you recognize words and characters, then you see more, you're able to process more. And what I've seen in companies, for example, in the onboarding process that my book also talks about, is that sometimes new people come into a code base. Maybe they're new to the programming language, maybe they're new to the domain or to the code base. And then a more experienced person shows them the code base. Like, this is where we initialize things, and here's a bunch of API calls, and here's some UX logic. And then to them, it is cat loves cake. It is all so easy. But then for a newcomer, they might literally not be able to see and process all the new things. For them, it might be the weird language that we had in the beginning, or maybe if they're a bit more experienced, the individual letters. So remember that if you're explaining something to someone and they don't have that much knowledge about the language or the domain, then they don't see it. It isn't like they're not smart and they can't think. It is just because they don't see it, right? You're not smart, not smart because you couldn't remember the first sentence. Like that was the mean trick that I played on you there. But this exact same process also happens in programming. What I want to talk about further, dive into a little bit deeper, is a concept called cognitive load. So imagine you would actually try to remember this first sentence, and it's shown here on the slide again. Then your brain sort of gets full, right? You're really like, a circle with a dot and a stripe and a sigma reverse and a diamond and a big C. It fills up your brain. You can almost physically feel that this is too much effort. That effort we call cognitive load. If your brain has to work really, really hard, then you're experiencing too much cognitive load. And cognitive load is also a topic that has been researched in science extensively, mostly by a professor called John Sweller that invented what we called cognitive load theory. The theory that your brain, too, like a processor, can be overloaded and too full to properly process again. Just like if your hard drive is full, then your computer doesn't operate so well anymore. So cognitive load theory describes that, and it doesn't just describe the fullness of the brain, it describes different types of fullness of the brain. Firstly, there is intrinsic load. So some problems are just inherently hard. We call this inherent complexity as well. And for example, if you have a triangle and you have to calculate the length of this third triangle, there's a certain complexity in that problem that you have to deal with. If you don't know how to square numbers, then you will never be able to find the solution to this. You have to know the Pythagorean equation to be able to solve this problem. We can't make the problem any easier. We can't make the problem so easy that it doesn't involve squaring and doing a root. That is inherent complexity, and that leads to intrinsic load that is part of the thing you're doing. But there's also a principle called extraneous load. This is load that is extra, that's coming on top of a problem. If we stay in the math space a bit, we have a programming example later. If we stay in the math space a bit, maybe you know that in many math books, problems are more commonly phrased like this, right? They don't put the numbers on the sides, they put the numbers somewhere else using a variable, and then there's extra text as well, like consider these values for Amy, extra fluff. You see that this extra information is making your brain fuller because you have to read this. This is going in your short-term memory. You have to do some processing because the 8 is the A, okay, and the B is the 6. This is taxing for your working memory, but it isn't really changing the problem, right? You're still doing the same equation. And then there's a third type of load called germane load. And germane load is good load. That's the type of load we want. You always need a little bit of room in your brain left to actually store information back into the long-term memory. So if your brain is too full, you can't remember anything. If you have a little bit of load left, then it's more likely that you will remember something. And so again, going back to the sentences, it's kind of likely that if I call you up tomorrow and I ask you what was the sentence, you will say, well, it was cat loves cake. You had processing power left to remember that sentence for the long term. Whereas for the first two sentences, it didn't even register. Your brain was so busy that there was no germane load left to store the sentence. So that's the thing that we use to store information in the long-term memory. Sweller did some spectacularly interesting experiments using cognitive load. In one of his papers that you see here, he had two groups of students do algebra equations. So the two groups did the same algebra equation, stuff you might know from high school as well, like A is 7 minus 4A. What is A? The first group just did the exercises. The other group got, as you see here, recipes for the exercises. So they got specifically information. Oh, if you have an equation of the shape A is B minus CA, what you can do is you can take the CA and move it to the other side of the equal sign, or you could always divide both sides by the same term. So they really got a recipe to how to solve the problem. And these recipes are called worked examples. And then they did the same equations as the first group. There was no difference between that. Sweller then compared how well these two groups of children did on these exercises. And the recipe group did way better. Which you might say, well, that's not very surprising because they got literal recipes, right? So of course they did better. But they also did better on different new problems. And that's kind of interesting because in programming, in many fields, we have this idea that you shouldn't give people recipes, right? If people are seeking information about your code base, you shouldn't just give them the information. You shouldn't just tell them how to get it. They should figure out how to find the information. And what Sweller discovered here is that if you have people practice recipes, practice worked examples, they actually learn strategies that they can then later apply in other problems as well, right? Because stuff that's in the recipes, like taking a term and moving it to the other side of the equal sign, but then flipping a plus to a minus, you can use that strategy in many different situations, not just in this specific exercise. So one takeaway here is that sometimes it can actually be good to give kids, but this is true for adults as well, to just give them a strategy, just to tell them this is how you do something, rather than have them figure out stuff by themselves. So what we think happens here, we don't really know everything about what happens in the brain, but the hypothesis here is that this group used their germane load to store strategies. They weren't so involved in the problems, just a little bit, just enough to also have room left to store these strategies, like taking a term from the one side to the other side, into their long-term memory, and then being confronted with different problems, they were like, oh, I know what I can try. These are some strategies I can apply. And the other group was so busy that they couldn't remember anything, just like you were very busy in the beginning with the complicated sentences. The big takeaway here is that you don't become an expert by doing expert things, right? It makes so much sense where you say, oh, if we want kids to be good problem solvers, we should let them solve problems. If we want people to be good programmers, we should just let them program a lot. But that isn't necessarily true. If you're somewhat of a beginner, then getting help, getting these trainer wheels in the form of worked examples, the recipes, is a better strategy for learning than just exploring for yourself. Only if you've really reached the expert level, it starts to make sense to learn by exploration. So now wrapping this all back up to programming, right? Because we talked about kids and we talked about math. What does extraneous and intrinsic load have to do with programming? So for programming, I would say that extraneous load is the most important load that you can do something with. If you're solving a hard problem, then it's just going to give you intrinsic load. But extraneous load is something that you as a programmer have some control over, because you can rewrite programs to fit your prior knowledge better. Remember when we had the algebra exercise, you can decide if you put the numbers here with the text, or that you take the numbers and you put them on the triangle. This is something you can do for code as well. And now we are at the core topic of this talk, a cognitive refactoring. Consider this code in Python. Suppose you are filtering out all customers over the age of 50. So that's what you want to have in a list. You're filtering in, actually. So you're taking all customers over 50. If you're an experienced Python programmer that has lots of experience with list comprehension, for you this is very easy. This is just cat loves cake. It doesn't take you any energy to read this code. But if you're not so experienced in Python, or if you haven't seen many list comprehensions, this might be tricky because it's sort of weird. There's something like a loop that is a for, but it's sort of in the middle of a list. What is going on here? And you can figure it out, but it will take you a lot of energy. What you could also do is rewrite this code, right? You can say, okay, so what happens here is I start with a list of names. First it is the empty list. Then I loop over customers. And if the customer age is bigger than 50, I add it to this new list. These two snippets of code are equal to each other. They're doing the same thing. But if you don't know list comprehensions, the second thing is a lot easier for you to process. And of course, this isn't about this specific snippet. Imagine we're in a situation which you have to figure out a larger code base. Then all of these list comprehensions are just gonna trip you up and not add anything, because they're far away removed from your own personal prior knowledge. So I call this a cognitive refactoring. It is a refactoring because the external behavior of the code is not changed, but it is not a refactoring as we typically use it that is meant to improve the structure of the code base. That's usually why we do refactorings. This is a refactoring you really do for you. You take the code, you move it towards your prior knowledge, you lower your own extraneous load in order to understand the code. And my book chapter has many different examples of cognitive refactorings. Another one is inlining a method. So from the perspective of readability, you want to have small methods that call each other. But from the perspective of understandability for you, a novice in this code base, it's actually not ideal if all the methods are linking to each other, because all of these hops where you have to take your debugger or you have to read through the code to find something, it's all adding to your memory. It's all increasing your cognitive load because it's all information you have to keep in your memory. What you can do, and many IDEs support this as well, is just take a method, you just inline it. You just take all the methods, you inline everything until you have a linear line of code. That is, of course, not preferred for maintainability purposes, but for understandability purposes, it can be really, really nice if you have all the information together, you get a sense of what's happening, and then, of course, afterwards, you just throw away this branch and you go back to the normal situation. So that is what a cognitive refactoring is, and that is why a cognitive refactoring is useful, because it helps you lower your own cognitive load. So that's it. That was my talk today. If you want to know more, of course, check out my book called The Programmer's Brain. I have a link at the end of my talk that has chapters. We sort of covered 2 chapters. Now it has a chapter about all these memory systems and what they mean for programming, and it has a chapter about cognitive refactoring, but it also has chapters about onboarding, code smells, variable names, but all from the perspective of cognitive science. As I said, that's everything I wanted to share with you today. If you want to know more, you can go to my website, feline.com, or follow me on Twitter under @Feline. If you want to know more about my book, or if you want to start reading straight away, you can go to feline.com/book. You can immediately buy the ebook that is already available at this time. You can also pre-order the print book that is set to come out somewhere this summer. Maybe you're wondering also, by the way, like what happened to the kids? So you started to teach kids and then you were failing and then you started this whole adventure into cognitive science. So what happened with the kids? Well, some of them dropped out, sadly, but many of them stuck around while I was improving myself. And out of this exploration that I did into cognitive science, two things came out actually. One thing that came out was the book that you can now order, but the other thing that came out was a programming language for kids. Knowing everything I know now about how kids learn and about cognitive load, I figured out that programming languages aren't really doing a great job of lowering cognitive load. So I made a programming language that's based on what we know about learning, called Hedy. So if you are teaching children or if you're considering to teach children, I'll be very honored if you want to check out my programming language as well. You can find the information on feline.com/Hedy, and Hedy is free and open source. So we're not selling you anything there. And Hedy is at this point available in many different natural languages: Dutch, English, Hungarian, Italian, Spanish, French. So wherever you are, your kids and you can enjoy Hedy in your own natural language. If you really like listening to me, there's one other thing you can do, because you could also listen to Software Engineering Radio. That's a podcast that I'm one of the hosts of. It's a weekly interview format where we interview people about building systems, about programming languages and databases, but also about soft skills that are related to programming, like how to do a job interview and how to get better at presentation or documentation. So if you want to check that out, SE Radio is available on iTunes and Spotify. Thank you so much, and I hope you enjoyed the rest of the Manning Conference today.